how to understand TCP/IP. Pretty much all of next week we're going to talk about TCP/IP. And I will only have time to give you the main concepts and main ideas of what's going on with TCP/IP. Everything is TCP/IP is carrying pretty much everything. Whatever you're doing right now, you're using TCP on top of it. So because IP doesn't do a lot, it carries messages. Everything else that gives you something where you can stream video or send reliable file transfers, that's all that. Alright, so TCP is at the transport layer. We're now going, this is layer 4. So remember the layering 1, 2, 3, 4, 5, 2, 3, 4. There are multiple layers. The main protocols there are UDP and TCP. Since recently there's some new protocols at the transport layer that pretty much try to fill the space in terms of functionality between TCP and UDP. They're not widely used. In fact, the main application, all the applications that you're using, internet applications that you're using, won't use them. But they're out there, and since a few years, and they may get some traction. We'll briefly talk about that in this part. So what I want to do is just, just get a feeling of what's going on at the transport layer, and I'll talk about something what UDP does. Pretty much doesn't do anything. Just port numbers and IP data. So the functionality is just, what I want to describe is one slide. What kind of stuff goes on? You take an IP datagram. What do you have to do on the transport layer? Well, the machine arrives at in the system, so now you have to deliver it to applications. To do that, you need to add a number to your IP datagram. That's the port number. And port number. That's what UDP does. Just sticking a port number in front of an IP datagram and calling it a UDP datagram. All right, so transport protocol. Yeah, so transport protocol does not see the message. The transport entity at the sending host just sees the other host. It doesn't see the message. Yeah? Which is good. That's taken care of by IP and by routing. Yeah? So IP finds the path to get to. That's what we discussed. The forwarding and routing. Yeah, routing sets up the routing table. Yeah, these are here the routers with multiple interfaces. So we have multiple in between. So we're finding the path using routing protocols, and then the forwarding piece of IP knows what to do to get to perform the routing table lookup. We're done with that. We're only seeing end to end. So transfer protocols are only realized at the end systems. So if you're sending, if you're doing something at the transport layer, the routers don't get involved. Routers also have a transport layer, so you can, when you log in telnet into a router, but then you're using the router, if you're telnetting into a router, you're using the router like a host, like an end system. So the two main protocols are UDP and TCP, just to get the acronyms out of the way. The User Datagram Protocol, and TCP stands for Transmission Control Protocol. So this is in a nutshell what they do. The UDP protocol is datagram oriented, like the IP datagram. That's the unit of delivery and transmission and reception in UDP. If an application program uses UDP, opens a UDP socket, creates a datagram, sends the datagram. That's the application uses UDP. Now TCP is stream oriented. Stream oriented means you're just writing, if you open a TCP socket, then you just write into it. You're just treating it like you're writing into a file. You're not creating messages. You're just sending an entire byte stream, and you're just popping, writing bytes here, write 100 bytes, 1,000 bytes, you just throw it into the open socket at the sending side. You don't worry about, at the TCP application center, does not worry about message boundaries. If you're receiving TCP, what you're doing is you don't have to parse packets, you just get application data. If you're streaming application bytes, that's called stream oriented. Yeah.
So which layer takes care of making sure that the data comes in the specified order?
That is what TCP does.
Oh, okay.
Yeah. So TCP has all these things. It provides a reliable, connection-oriented byte stream.
So TCP is the one that gets all the packets and puts them in the order that.
Yeah. Just look at the headers.
Okay.
If there is a header field for sequence numbers, it can put things in order. You will see UDP doesn't have sequence number in the header, so it cannot, things are out of order. It doesn't, there's no order. Each datagram is, each UDP datagram is its own. So if you're doing ordering here, you have to do it at the application layer. TCP is reliable connection-oriented. UDP unreliable connection. If you remember what IP, the IP delivery service, the lower layer. That service here, down here, the service that IP provided is connectionless and unreliable, meaning there is no notion of sequence. Unreliable means there's no delivery guarantee. The best effort service. So that's the same service that UDP provides, telling you that it doesn't do a whole lot. The implementation is very simple. One thing that it does that TCP does not do, it does both unicast and multicast. So what you do is you can send a UDP datagram to multiple destinations if you're using a multicast IP destination address. These are these class D addresses. We cover multicast separately. You cannot do it. It only exists as unicast, meaning TCP is always between two endpoints. Let's see. So TCP pretty much is used by most internet if you're using the web, email, file transfer terminal. UDP is used a lot for network services. DNS, even though DNS can also run TCP, but mostly using UDP, routing protocols such as RIP. We saw that we were using UDP, SNMP, routing protocol. Actually, we saw that BGP belongs into this category here. It uses TCP, network management. Sometimes streaming applications use UDP. Streaming applications, media streaming. But if you these days, if you're streaming from a server, it also sent as TCP. All right, so that's the overview here. So just the header format. So have in mind, UDP sends messages, very simple protocol, doesn't do a lot. TCP, turns an unreliable IP network into a reliable service, turns a connectionless IP datagram service into a connection-oriented service. That's where a lot of the work needs to be done. So as I said, the UDP datagram is just very simple. The header has just 16 bytes, just 8 bytes. There's a port number for the source, destination port number. That's what it does. Then it has a simple checksum on the header. It's the same like the IP checksum, and then a UDP message length, which then indicates the length of the what's called. That's pretty much it. Message length. So the port number identifies an application. The TCP header is longer. It also has a source port and a destination port number. The port number indicating application programs. Think about like a port, like a mailbox like a conduit where the application program talks with the IP stack. Application, a web server, opens, attaches itself to port 80. So if you're sending something to a machine at port 80, TCP will stick it in port 80, the web server then gets it from there. So that is essentially the port number providing them the possibility to have multiple application programs on the same system receiving data. What's more, there is a sequence number. Yeah? So now you can talk about sequence. What is interesting is the sequence numbers is 32 bits. Well, that's a large number. 2 to the 32, 4 gigabytes roughly. What TCP does, it assigns sequence numbers to bytes in the byte stream. It doesn't have sequence numbers for packets. It has sequence numbers for bytes. The numbers that bytes came in the application data. Acknowledgements. Now this is for reliability. You're sending something, expecting an acknowledgement. We'll talk about that in detail. Let's see. Flags. Yeah, they're quite important. Window size used for flow control. Urgent pointers is not used a lot. It's just something where you can point an offset in the application part of the payload, where you can point to urgent data. Checksum, yeah. And then options. Options are actually used quite frequently. There are quite a few options that we should talk about. What's that? TCP handle 25 stop. Yes.
So if you have 2 packets, and the first sequence header in the first packet is 10, and the payload is 20, so the second packet's sequence number should be 30 in that case?
No, okay. So think about the application numbers, the application data that the user is sending being numbered. Each byte has a number. So now here you put in the number of the sequence number and the number of the first byte in that packet.
Why is it done like that?
Why is it done? Because TCP sends bytes, deals with, let's see, just give you a scenario. It's a good question. Okay, so this is here the sender, this is the receiver, yeah? Receiver, sender. So now I send data in here, I send, and the data is received here. Here we have TCP at the receiver, TCP at the sender, yeah? So let's say there are 100 bytes being written into it. TCP can now send, just writing 100 bytes in here. The sender, TCP pretty much decides how these packets are sent. So what it can do, it can send 2 packets, one with 30 bytes and one with 70 bytes. If you're asking for retransmission, it could send them as 50 bytes. And so the numbering is what it does is here we're just dealing the numbers, just the numbers that are written in here. They are just sequentially numbered, and then they're somehow transmitted. Yeah. In fact, in reality, this doesn't happen because ultimately for efficiency, TCP does not, once it cuts packets in a certain. No, I shouldn't be saying that. TCP really does not care. It really looks at the byte stream.
It's like fragmentation that we learned for IP. It's like fragmentation that we learned for IP.
Well, fragmentation is if something is too long and then you cut it into smaller pieces. Here you're getting essentially a worm. Let's suppose somebody is writing a file into a socket. Yeah, what TCP does, it just chunks it up in pieces and sends them out. And then it keeps track of the sequence numbers that are in each chunk. Yeah? And then the receiver sends acknowledgements acknowledging certain numbers. Now we'll get really down to the details of this. Then there's something else. This is something that is what TCP does. It controls, performs control. It controls. TCP tries to use all the available bandwidth, but doesn't try to send more than is available. There's an algorithm in TCP where signals from the network and from the receiver are used to adjust the amount of data that can be sent. That's it's a great property of TCP. So the receiver can tell the sender. The receiver can tell the sender, well, don't send me, you can send me 1,000 megabytes. That's done with the Windows stuff. So that you've learned in 361 about the sliding window flow control. And TCP uses a version of sliding window flow control that we discussed. It's a little bit more, it's always more tricky than an introductory lecture, but it's basically a plain sliding window flow protocol. It's a little bit because it's done at the byte level. Now we'll just see how this goes. So that's the TCP header in a nutshell. So what both protocols do, TCP and UDP, by just any transfer protocol, they add port numbers. Yeah? And the way to, as I mentioned, what happens is user processes use a protocol attachment sets to port numbers. Yeah. Maybe this is just a layer image to show us here how the port numbers work. This is, Oh well. So if you have multiple processes running on a system, what you're having, IP receives everything destined to receives everything sent to an IP address. Then IP looks at the protocol field, decides if it's TCP or UDP. Once you're in TCP, you're looking at the port number, and with that port number, you can identify the server process. Actually, TCP does not care about the user process. In between is the port number. TCP writes into the port, puts something into the port number. The process is then reading from that port number, and that's how the communication takes place. Yeah, so you have to know this idea that the port is really, this is where is used as the service access point where application programs access the TCP/IP protocol. All right, so UDP. Yeah, so UDP, just 2 slides I have, I guess. Unreliable transmission of datagram. It pretty much extends the service of IP to an application to application service, and that is done by the host-to-host service of IP. It's being enhanced by application to application service, and that is done by adding port numbers. That's pretty much it. It provides multiplexing and demultiplexing information. So if you're getting a packet in UDP, you're looking at the port number, you demultiplex. You demultiplex number that kind of process. All right, let's briefly talk about some newer protocols. So it turns out that this space here, UDP provides very little. TCP provides a lot. For example, what is not provided here is something, a service where you say, well, I want to send single packets because my service is established, but I want them to be sent reliably. I want to be short delivery, meaning you need acknowledgement. Another thing that one may want to have is you may want to have, what else is missing here? I want to send a data stream. But, so I want to send streaming, I want to have sequence numbers, but I don't need reliability. Like a voice over IP protocol could greatly benefit from that. Skyping over TCP, the retransmission of a voice channel doesn't really help. If the retransmission takes too long, interactive voice is very delay sensitive, so data, you cannot just hold data back if something is missing. You have to send it to the application. So the application notices that there is some data missing. So if you're retransmitting it, it comes in later, it's too late. And so you want to have sometimes streaming services that are not reliable. Stream-oriented service that is not reliable. Also something that is what TCP does, as I mentioned, it reacts to network congestion. If the network is loaded, TCP backs off. UDP never backs off. UDP never backs off. So because of that, what one may wants to have is a service that is packet-oriented, datagram-oriented, but which somehow does not ignore congestion in the network. Because if the network is congested, you keep on sending, you're making matters worse. There's no interest in that. Yes.
What happens when you back off?
Yes.
Does it close the connection or?
No. TCP just goes back and sends very little. It's a very interesting algorithm. So TCP uses, how does TCP know that the network is congested? It takes a loss. If a packet gets lost, it believes that it is because of congestion. If that happens, it pretty much stops sending and then starts again very slowly. What it means is the window size being the amount of data that can be sent without waiting for an acknowledgement, the window size is reduced to 1, and then it's built back up. It's a very nice algorithm called slow start congestion avoidance, where TCP is always adding, it's always increasing the rate at which it's sending until something bad happens, and then it backs off, and then it does this again. So it's always trying to increase the rate until something bad happens, then it backs off, sets its rate to a single packet, and then continues again. We'll learn about that next week. So a lot of in between. So these are what these new protocols are about. This one you have to think about these. There is the SCTP protocol, the DTCP protocol is exactly one of these services that I mentioned. SCTP, what does SCTP stand for? Stream Control Transmission Protocol. DTCP, Datagram Congestion Control Protocol. You already see it, yeah? So DTCP is essentially UDP with congestion control. And SCTP is like TCP for datagrams. I send messages, but I get them delivered full duplex, and I have pretty much can have them as reliable transmitted. We can have ordered and reliable datagrams. So we have sequence numbers added here. And it reacts to congestion control. Now this is something, congestion control, this also has congestion control. So these days one would not design it because it turns out that having congestion control mechanisms, these are mechanisms by which the sender backs off when the network gets full. These are essential for having a well-functioning network on a large scale. The reason that we have that the internet is working so well is really the congestion control, due to the congestion control algorithm of TCP. It's very dangerous to work kind of fiddle with it, even though it's done, and it's done. If you would turn congestion control in TCP off, the internet would collapse. Congestion really. And that's really like running into this called the congestion cliff. The performance really goes down. We'll see the next one. So the idea for when do you need kind of what is the main application here? Signaling in telephone networks. Signaling in telephone networks. That is the message. These are the messages that are the messages that set up your phone call. You're using your phone, it's something physical, but at your local office, the telephone call is set up by packets. Now these packets, they're using a protocol which is really old, called the Signal SF7, Signal System 7. It's a packet-oriented protocol. It's not IP-oriented. Well, so people thinking about transitioning the signaling for the telephone network to TCP/IP. However, UDP has not a good enough service. So that's the main application. For the UDP, the congestion control, it's pretty much for applications that transfer large. You're having a message-oriented interface. This is too general. And because it's an unreliable protocol. So we take that a little bit further. Anyway, so just for what it's worth, we're not discussing this in detail. These are the packet formats. What HTTP does is you can have multiple, have substreams in the data flow. It's not that anyway, so just to give you a flavor that there's more coming, and so these protocols here, to my knowledge, there's no other protocol that is a transfer protocol that is currently being developed. So these were standardized very recently, 2006, 2000. TCP is from 1974, and UDP, we don't care about it. That's been there forever because it's just IP data. All right, let's see. So now I can start the part on TCP. So maybe this part is the least interesting. Next week, I promise it gets more interesting. Yeah. Okay, maybe not so much. What can I say? It is what it is, and we have to discuss these pieces. All right. This is the issue of this is how you have to think about TCP. The TCP sender, TCP receiver. You're sending, essentially, you're piping data into a TCP connection. TCP chunks, cut these packets into chunks. These chunks are called segments. Even if you hadn't paid attention, it was not on the slide. They're called segments. In data. The byte stream is broken up into chunks, these are called segments. So TCP packets, they're called segments. Each segment is put into an IP data. Simple enough. TCP is connection oriented. What that means is essentially a client-server type of interaction. Server is the passive part. Client open a connection to the server. Server acknowledges, then the data transfer starts. Once the connection is set up, it's not important who's the client and who's the server. For TCP, client server is only relevant for opening the connection. The server has to be opened first. Somebody has to, for a connection, somebody has to be ready and waiting for something. That's the server. The active part is the client. Once the connection is in place, the connection is bidirectional. You can have more data come from the client to the server, or more data from the server to the client. It does not matter. When you close a connection, it also doesn't matter. Either side can be first. All right, so the the server is waiting for a connection request. Client requests the connection, the server accepts the connection, and then the data transfer takes place. And at the end, there can be a disconnect. The disconnect can also be initiated from the server. In fact, TCP treat the two disconnect requests separately. It's called a half close. Both sides, after both sides have a half close, then you close. Reliable means that the reliable string means that the receiver sends acknowledgement so his packet is sent as segment. The receiver sends acknowledgement for the segment, but the acknowledgement indicates sequence numbers. TCP maintains a timer. If it has a retransmission, it has a timer for the transmission of it. If the timer expires, it retransmits. You've learned that in 361. If you remember the schemes, go back N, selective repeat. Yeah? So TCP essentially does go back N. It also allows selective repeat, but it has to be negotiated during connection setup. That is something that was added maybe 15 years ago, but it's not really. Let's see. How are errors detected? Well, there are checksums. Okay, that information is not really. The errors are detected essentially by receiving sequence numbers with holes that indicate to a hole. That's one way to detect an error. If you're sending me acknowledging 100 bytes, if you're acknowledging to me the bytes from 0 to 100, and then you're acknowledging to me the bytes from 200 to 300, but you never acknowledge 100 to 200, TCP at one time thinks that has been lost and retransmitted. The other one is I'm sending 0 to 100, you never acknowledge. Then my timer kicks off, I retransmit. Yeah? So that's how this will roughly goes. At this level, it's fine. We're going into more detail. So the byte stream service, yeah. So what you have is TCP handles data in segments. Yeah, TCP transmits segments. Yeah, and when I say they transmit in this way, it sends the segments to IP, which then delivers them, puts them in datagrams. To the higher layer, TCP handles data in a sequence of bytes. So what you now can have is this. The application does not see any segment boundaries. In TCP, if you're writing 100 bytes in here, then 20 bytes in here, the segments are just, the applications are not concerned with how the segments are constructed. In fact, so what the data is then pretty much going from a TCP buffer into a buffer at the receiving side, and then the application can receive 40 bytes, or you can receive the data in different single bytes. Just reads it like a pipe that is filled with bytes. Just reads it like from a, that's what I said, you read it like you're opening a file and then you're reading the bytes from a file. The same concept is what TCP provides. And actually, if you're programming Java, if you're programming Java, you're opening in Java the sockets. At the application program, you open a socket. Then a socket is an application buffer between the kernel and the application. Then you bind a socket to a port number. That's when the coupling from the application side takes place. Now in TCP, if you use it in Java, if you're using UDP, the socket is called a datagram socket. Have you heard this program in Java? What happened to programming? See, so see the string socket. The string socket uses C++. Who's done C++?
Yeah.
C++. So let's talk C++. String socket uses TCP. Datagram socket uses UDP. That's it. Yeah. So whenever you open a string socket, you use TCP. And if you have a string socket, you're just sending it, you're not done. You're just writing your stuff in there. You're like you're writing into a file. Opening a file or reading from a file or reading from a string socket has the same level of complexity. You're reading whatever you want to do. All right. So the header format we already discussed. A lot of these bytes. That's when we see something one system. So the port numbers, let's send the port numbers. Almost there. Yeah. So application opens a socket, binds the socket to a port number. Then if somebody sends to that port number, the application can read from that port number and get the data. That's how this system is. Now, sequence numbers. The sequence number, the acknowledgement number. Sequence number 32-bit long, so you're going from a 232, it goes, roughly 4.3 gigabytes. Sequence numbers count bytes. And the content of the sequence number field, I think I mentioned that earlier, is the sequence number of the first data byte that is in the payload of the segment. The first data byte. And then you have to, of course, know what's the last one. Well, you can compute it. How can you compute it? Well, you're looking at the length field in the datagram, and then you look, oh, there's no length field. So how do you know the length? There's no length field. It's a header length. Well, IP header had a length field. Yeah, so you know how long then you're subtracting the header length from IP, then you're subtracting the header length from TCP, then you know how much payload you have in here. Yeah, payload being the user data. So this is the raw user data. That's what I'm really running here. Now, how do you start? You always start with number 2. So what TCP does is the first byte that is sent is a random number between 0 and 2 to the 32. That's the initial sequence number. The initial sequence number is negotiated at the beginning of a connection. Not negotiated. The client and the server that tell each other, this is the number that I'm going to start with. And that's a random number. And there's a reason for that. Yeah, so randomly select. Then the acknowledgement number. So acknowledgement, we say more, let's see. Acknowledgements are piggyback. So if you're having a data flow, if we're looking at a packet here that is coming from the sender to the receiver, the sequence number, you're sending a packet in this direction. The sequence number contains it's the number of the packet that comes from the sender. The acknowledgement number in this packet would be an acknowledgement for data that the receiver sent to the sender. So you're sending, if you send data and you set the acknowledgement number, using the acknowledgement number, you acknowledge the numbers in the reverse direction. So that's called piggyback. You have heard that. Yeah? So let's say, if you didn't have that, you would need separate acknowledgement packets, so just efficient. If you don't have data in the reverse direction, well, then you only send a header. So an acknowledgement packet without data, that exists. Actually, it exists out of it. When it's not always the acknowledgement data. If the data in the acknowledgement field has meaning, then there has to be a flag set. So the flags are actually, these are the flags, actually very important. And you have to know there are 6 bits. And some of them are extremely critical. They pretty much tell you how do you know that you request an opening of a connection? Well, it's a flag that plays that role. How do you know that the acknowledgement number here has meaning, that you're sending an acknowledgement, that a packet carries acknowledgement information? It's also a flag being set. So in this case, it is the X flag. The meaning of acknowledgement is, well, if the number is in the acknowledgement field is 1501. What this means is you're acknowledging everything, but not including byte number 1501. Yeah, so 1501 acknowledges everything until 1500, but is not including 1501. So the acknowledgement number is always, this is what I expect as the next number. I acknowledge, if I say a number, I acknowledge 53, that means the next number that I expect is 53. I have received everything up to 53. One has to get used to this, but that's a convention that is used since the 70s in all these kind of acknowledgement protocols. And it goes well with the way you think about this. Let's see. Sliding window. Header length. This is the length of the header in 4 bytes. It's kind of the same thing that we have with the IP header. Headers are 4 bytes long. These are the flags. The urgent flag, so there are 6 flags. The urgent one means kind of what the urgent point, the urgent flag means that this pointer here has meaning. Not really important. The X flag is important. It says that the acknowledgement number contains meaningful data. That means that the receiver of the data needs to parse it. The push flag is used, you will see if you're using Wireshark or TCP, the push flag is set a lot. It tells the push flag, if the segment has the push flag set, that means that the receiving part of TCP should write the data into the application buffer as quickly as possible. Notification from sender receiver that the receiver should pass all data that it has to the application. So it should not be laid internally. Yeah? So you will find that it's normally set. The reset flag, RST, the reset flag is used by to terminate a connection. Either side can do it. Reset flag terminates the connection. It's the same if you're using in a shell, you're opening a telnet connection, then you hit Control C. Just terminate the connection. Now resets it, goes back to 0. The SYN bit, this stands for synchronized sequence numbers. What it really is, the SYN bit is used for opening a connection. If a packet is sent with a SYN bit set, that is a request for open a connection. The reply to that from the server is a SYN bit set and an ACK. SYN, ACK, ACK. These are the 3 pieces that open a connection. The fin means send is finished with sending. This is used for closing a connection. If a TCP connection, either the client or the server sends a packet with a fin bit set, it means it has no more data to send. The first one who does this on a connection will still keep open because the other side may have data to send, and it has to acknowledge. Fin does not mean you're shutting down. It's an orderly closing of a connection. It's just done in 2 parts. One side does it first, that's the active closing. The other part, the second is the second part that when it's done will also send a packet with the fin bit set, which closes that part. Both have to be acknowledged. All right. Window size, okay. So that's pretty much the options. What is important in the options, when a connection is opened, options are not used a lot unless in the packets that open a connection. There's a lot of data being negotiated in the opening of connection. What's your initial windows? What's the initial sequence number? That's sent in the sequence number field. Pieces that are communicated is the maximum segment size, the MSS. What's your maximum segment size? This is my maximum. This is my maximum segment size. Then you can send. So this is you can use the maximum segment size relates to the MTE. to the MTU, the maximum transmission unit that we see at the IP data link layer interface. The maximum segment size is related to it. That's pretty much the largest segment that can be sent that will not cause fragmentation at the locally, and you don't know what's happening. All right, more options here. The window scale option. Yeah, this is something that you see more now these days. Yeah, the window scale option. That's something one did not used to see a lot, unless in satellite communication. It is possible to increase the TCP window size from 16 to 32 bits. So what this means here is the window size, you see it's 2 bytes long. That means the maximum window is 65,000 bytes. If you're sending data over long distances at high rate, 65,000 bytes is not a lot these days. So what's happening is you're sending these 65,000 bytes and then you have to wait for acknowledgements to come back. The throughput of a TCP connection can be limited by this. So there's an option that can be it's used during the opening of a connection normally that says, well, the window size, interpret this as multiplied by 65,000. So then you can have window sizes of 4 gigabytes. No.
高中学弟。
打招呼啊。
You see what's going on there. So it's not science, it's just tidbit stuff, yeah, but it's all TCP. Really, it's worth. You could study it for a whole semester. There's a lot to know about. So let's see. Actually, in the lab next week, what's called you see the window scale option. Yeah. So this window scale option then increases. Can only be used in the SYN segment, yeah, which means during the opening of the connection. All right, let's see. That's as far as I want to go. The next thing I'm going to do is talk about the opening of the connection management. Connection management is essentially the process of opening and closing a connection. And so this is a state diagram here. So you can get from a closed to an established connection, and there's a sequence of events that gets you from established to closed connection. We discussed that on Monday, and then we go into